Hi! Today we're going to learn about the divergency test for improper integrals. Let's say we have to prove that the integral from 1 to infinity of 1 over x minus 2 dx, or it should say dx, is divergent. So dx is divergent. So before we get started, let's just try to picture this in our head. How would we figure out whether an improper integral was divergent if we didn't already know that it was? So we don't know right off the top of our head whether 1 over x minus 2 is divergent. So how do we do that? Well, let's look at an example. Let's say that we had one function like this. And let's say that we wanted the integral from here to infinity. So this is, let's say, 2 to infinity. So this is f of x, and we want the integral of from 2 to infinity of f of x, 2 to infinity, of f of x dx. So let's say that we knew that what this area would be. So we know this is a common function, so let's say f of x was a common function. So we would know, based on this example, based on this example, we would know that the area of f of x under the curve from 2 to infinity would have to be infinite, right? So this would be divergent. Now let's say we had this other random curve. So we have this other random curve, g of x. And let's say that we wanted to find this, the area under the curve from 2 to infinity of that. Or actually, let's just say that we didn't want to find that, we just wanted to know whether it was divergent or not. And let's say that g of x is an integral that we cannot compute by hand or analytically. How would we do that then? Well, if we know that g of x is greater than f of x for all x values, so all of the y values of g of x from 2 to infinity onwards are greater than all of the f of x values, then that means that the area of g of x from that part, from 2 to infinity, will also have to be greater than the area from 2 to infinity of f of x. And if the area of f of x from 2 to infinity is infinite or divergent, then that means that the area from 2 to infinity of g of x is also infinite or divergent. So that would mean that g of x is divergent. So let's make a rule for this. So if g of x, let's say g of x is what we want to find, so let's say that we want to find whether g of x is divergent or not divergent, then we would say g of x, the function that we want to find, if g of x is greater than or equal to f of x, but now we need a specific domain. So how do we do this? We want to know from 2 to infinity, right? So this would be if the integral from 2 to infinity of g of x is greater than the integral from 2 to infinity of f of x, then that means that, and f of x is divergent, or this integral is divergent, then that means that this integral has to also be divergent. So one thing to clear up is that we're not saying that the integral is greater than the other integral, although it has to be greater than the other integral. And the reason why this has to be greater than the other integral is the condition that we want to set. So this only works when g of x is greater than or equal to f of x for all x values, so for all x values on the interval of the integral. So basically, if g of x is greater than or equal to f of x for all x values on the interval of the integral, so in this case from 2 to infinity, then that means that, and if we know that the integral from 2 to infinity of f of x is divergent, then that means that the integral from 2 to infinity of g of x would also be divergent. So take a moment to go over this and then we will solve this problem. Okay, so if you didn't get it, you can pause the video here or go back. But now we're going to erase it. So here in this example, we get that our g of x function, or the function we want to figure out whether it's divergent or not, is 1 over x minus 2. So how do we find a function that is less than or equal to 1 over x minus 2 on the interval from 1 to infinity? Well, that's easy. We just find the function that is smaller than g of x. So the function that would be smaller than g of x would be f of x. And we have to know if this integral is divergent. So we need to figure out an f of x that is also divergent and less than this. And if there's none, then that means that it fails the divergency test for improper integrals. So one example would be 1 over x. So as we can see, because both of them have the same numerator, and however this denominator is bigger than the g of x's denominator, then that means that f of x is greater than g of x. And so that means that therefore, from 1 to infinity, so for positive numbers, the denominator from 1 to infinity, f of x is greater than g of x. So, now let's figure out whether f of x is divergent. If it's not divergent, then we have to pick out another number, or another function, sorry. So, the integral from 2 to infinity of 1 over x dx, so we can just say dx over x, would have to be the natural log of x. So we have the natural log of x, and we have it from infinity to 2. So this would be equal to the natural log of infinity minus the natural log of 2, which would be equal to the natural log of infinity would be infinity minus the natural log of 2, so infinity minus a constant would just be infinity. So because this is infinity, that would have to be divergent. So if f of x is divergent, and we know that g of x is greater than or equal to f of x on all the x values of this interval, so g of x is greater than or equal to f of x for all values on this interval of the integral, then that means that g of x, and we know that f of x is divergent, and because we know that f of x is divergent, and f of x is less than or equal to all of the y values of g of x on the interval from 2 to infinity, then that means that g of x is also divergent. So, today we learned about the divergency test for improper integrals. Thank you for watching this video.